In this video, we are going to solve some problems under the reduction formula. So we have this problem that says that if I of n is equal to integral of 0 to 1 of x exponent n square root of into bracket 1 minus x dx, prove that into bracket 2n plus 3 I of n is equal to 2n I of n minus 1, and hence find I of 9. So I of n is equal to integral from 0 to 1 of x exponent n square root of 1 minus x dx. You see that we can easily integrate square root of 1 minus x dx, and then we can differentiate x exponent n. So in this case, let's let u to be equal to x exponent n. So du is equal to, bring n down, x exponent n minus 1, then dx. So let's let dv to be equal to square root of 1 minus x dx. We can rewrite this as equal to into brackets 1 minus x exponent 1 over 2 dx. So if you integrate this, you see that we first have to bring, so v is equal to, bring minus, because if you differentiate 1 minus x, you get minus 1. So minus has to come out. Then you add 1 to half. That will give us 3 over 2. And if you divide by 3 over 2, we have to multiply here by 2 over 3 into bracket 1 minus x exponent 3 over 2. So this is v. So I of n is equal to u v, which becomes x exponent n times minus 2 over 3 into bracket 1 minus x exponent 3 over 2, evaluated at 0 and 1. Then minus integral of v du. So v is minus 2 over 3 into bracket 1 minus x and exponent 3 over 2. Then du, this is our du, times nx exponent n minus 1 dx. So let's compute this. If you put 1 here, 1 minus 1 is 0. So that will go to 0. And if we put 0 here, because of this x, that will also go to 0. So I of n is equal to, this goes out, but there's minus here and there's minus here. So, and then n is also a constant. So let's pull it out. We are left with 2 over 3 n. So this is integral 0 to 1. Integral of 0 to 1 of, into brackets, 1 minus x exponent 3 over 2, then times x exponent n minus 1 dx. We established that I of n is equal to 2 over 3n integral of 0 to 1 of, into bracket, 1 minus x exponent 3 over 2, then x exponent n minus 1 dx. So I of n is equal to 2 over 3 n integral of 0 to 1. Now this 3 over 2 is the same as 1 plus 1 over 2. So we can rewrite this as 1 minus x exponent 1, then times 1 minus x exponent 1 over 2, x exponent n minus 1 dx. So I of n is equal to, we can break this integral into 2. So it becomes 2 over 3n integral of 0 to 1. Then we have 1 minus x, but exponent half, so that becomes square root x exponent n minus 1 dx. Then you see there's an x here, so minus 2 over 3n integral of 0 to 1. Now this x will multiply this x, so x exponent n minus 1 will be left with x exponent n. So here will be x exponent n, then square root of 1 minus x dx. So if we rewrite I of n well, find out that I of n is equal to 2 over 3n integral of 0 to 1 of x exponent n minus 1 square root of 1 minus x dx minus 2 over 3 n integral of 0 to 1 x exponent n square root of 1 minus x dx. So I of n is equal to 2 over 3n. So all of this, remember, I of n is equal to x exponent n square root of 1 minus x. So I of x exponent n minus 1 becomes I of n minus 1, then minus 2 over 3n. Now, here's what we started with, I of n. So let's multiply through by 3. So we get 3I of n is equal to n I of n minus 1, then minus 2n I of n. So let's bring I of n to the other side. So we have 3I of n plus 2n I of n is equal to n I of n minus 1. But sorry, here's 2n, because here's 2n. So here becomes 2n I of n minus 1. So we can factorize I of n out. So this becomes 2n plus 3. Then I of n equals 2n I of n minus 1. So this is what we're asked to prove from the question, because we're asked to prove that this integral is 2n plus 3 I of n equals 2n I of n minus 1. So for the next part of the question, we are supposed to find I of 9. But we have been able to establish that 2n plus 3I of n is equal to 2n I of n minus 1. And then from the question, we are given that I of n is equal to integral of 0 to 1 x exponent n square root of 1 minus x dx. So I of 9, that means that n is equal to 9. So if you put 9 here, you see that 2 times 9 is 18. 18 plus 3 is 21. So 21 I of 9 is equal to 2n. So 2 times 9 is 18 I of n minus 1. So I of 9 is equal to 18 over 21. Then I of n minus 1 becomes I of 8. So let's find I of 8. But for convenience sake, let me just rewrite I of n as equal to 2n divided by 2n plus 3 I of n minus 1. So I of 8 is equal to 2 times 8 is 16. Then here becomes 16 plus 3 is 19. I of 7. Then I of 7 is equal to 2 times 7 is 14. Divided by 14 plus 3. That becomes 17. I of 6. And then I of 6 is equal to 2 times 6 is 12. And then 12 plus 3 is 15. I of 5. I of 5, let's continue from here, is equal to 2 times 5 is 10. 10 plus 3 is 13. Then I of 4. And I of 4 is equal to 2 times 4 is 8. Divided by 8 plus 3, that is 11. I of 3. And then I of 3 is equal to 3 times 2 is 6. Then 6 plus 3 is 9. I of 2. And I of 2 is equal to 2 times 2 is 4. And 4 plus 3 is 7. I of 1. And then I of 1 is equal to 1 times 2 is 2 divided by 2 times 2 plus 3, that's 5. I of 0. Then I of 0 is equal to, now if you put 0 here, we are going to get integral of 0 to 1 of x exponent 0 is 1. So we are only going to be left with 1 square root of 1 minus x dx. But we already know this answer because that is what we did for the VIN. So in that case, we said VIN was equal to minus 2 over 3 into bracket 1 minus x exponent 3 over 2. All of this evaluated at 0 and 1. Now, if you put in 1 here, you will get 0. So I of 0 will be equal to, if you put in 0 here, we will get 1 exponent 3 over 2, which is 1, and then times minus 2 over 3 will give us minus 2 over 3. So we've gotten I of 0. So what we will do is that we have to put I of 0 back into all of this to find I of 9. So when we do that, we find out that I of 9 is equal to, so we started with 18 over 21. So 18 over 21, then times I of 8, but I of 8 is 16 over 19. So 16 over 19, I of 7. And then I of 7 is 14 over 17. I of 6. I of 6 is 12 over 15. I of 5. And I of 5 is 10 over 13. I of 4, which is 8 over 11, times I of 3. I of 3 is 6 over 9, times I of 2, which is 4 over 7. Then times I of 1, which is 2 over 5, times I of 0. And this I of 0 we got as, sorry, here is not minus, here is plus, because it become minus, so here is 2 over 3. So times 2 over 3. And when you do all of this, you find out that I of 9 is equal to 0.027. So let's solve this problem. I of n is equal to integral of 0 to pi on 2 sine x exponent n dx. Show clearly that a, I of n is equal to n minus 1 over n, I of n minus 2 for n greater or equal to 2. And then b, integral of 0 to pi on 2 sine x exponent 6 into bracket 1 plus cos squared x dx is equal to 45 pi over 256. So let's start with I of n. I of n is equal to integral of 0 to pi on 2 of sine x exponent n dx. So let's rewrite this equation as I of n equal to 0 to pi on 2. That is integral of 0 to pi on 2 sine x exponent n minus 1. And because I put n minus 1 here, I must multiply by sine x dx. So now we can differentiate sine x exponent n minus 1 and integrate sine x. So our u is equal to sine x exponent n minus 1. So du is equal to, bring n minus 1 down and multiply by sine x exponent. Now n minus 1 becomes n minus 2. If you differentiate sine x, you get cos x dx. And then our dv is equal to sine x, in this case dx. So v is equal to, if you integrate sine x, you get minus cos x. So I of n becomes u v. U is sine x exponent n minus 1, and then times v is minus cos x, evaluated at 0 and then pi over 2, minus integral of v du. V is minus cos x, and then du is into bracket n minus 1 sine x exponent n minus 2 cos x dx. So I of n becomes minus cos x sine x exponent n minus 1, evaluated at 0 and then pi over 2. Then minus minus will make here plus, integral of, but before we write that, let's bring n minus 1 out. Integral of cos, now here's cos x, so this becomes cos squared x, then sine x exponent n minus 2 dx. So let's evaluate this. So I of n is equal to, if we put in pi on 2, so cos pi on 2 is 0. So then now if you put in 0, sine 0 is 0. So all of this part goes to 0. So I of n is only left with, into bracket n minus 1, integral of cos squared x, then sine x exponent n minus 2 dx. The next thing is that we know that from trig identities, cos squared x is equal to 1 minus sine squared x. So let's replace cos squared x with that and continue. So let's continue from here. So I of n is equal to, into bracket n minus 1, then, but here is integral of 0 to pi on 2. So integral of 0 to pi on 2. then cos squared x, which is 1 minus sine squared x, then times sine x exponent n minus 2 dx. Having written this, we can break this integral into 2. So I of n is equal to into bracket n minus 1, the integral 0 to pi on 2 of sine x exponent n minus 2 dx, then minus into bracket n minus 1, integral of 0 to pi on 2. Now, here is sine squared x, here is sine x exponent n minus 2. If you do that multiplication, we'll be left with sine x exponent n dx. So, I of n is equal to n minus 1. Here is I of n minus 2, then minus into bracket n minus 1. Then this part is I of n. So let's expand. I of n is equal to into bracket n minus 1 times I of n minus 2, then minus n I of n, then plus I of n. So this I of n and I of n will cancel out. So if we bring minus ni of n to the left hand side, we have ni of n equals into bracket n minus 1 I of n minus 2. So if we divide through by n, we find out that I of n is equal to n minus 1 over n I of n minus 2. And that is exactly what we are asked to prove. So the B part says that we should show that integral of 0 to pi on 2 of sine x exponent 6 times into bracket 1 plus cos squared x dx is equal to 45 pi over 256. And then we know that I of n is equal to integral 0 to pi on 2. So here is 0 of sine x exponent n dx. And by our reduction formula, we already obtained that I of n is equal to n minus 1 over n I of n minus 2. So what we need to do is to express this integral to look in this form, that is sine x exponent n. So let's break this integral into 2. So the integral becomes integral of 0 to pi on 2 of sine x exponent 6 dx, then plus integral of 0 to pi on 2 of sine x exponent 6 and then cos squared x dx. So now this cos squared x, we can further break it. So this is equal to integral of 0 to pi on 2 of sine x exponent 6 dx, and then plus, now integral of 0 to pi on 2, here is sine x exponent 6, then cos squared x becomes 1 minus sine squared x dx. So here is integral of 0 to pi on 2 of sine x dx. Then let's break this integral into 2. Then plus, sine x exponent 6 dx. Then plus integral of 0 to pi on 2 sine x exponent 6 dx. Then minus integral of 0 to pi on 2. Now here sine x exponent 6, sine x exponent 2. So we will get sine x exponent 8 dx. So at the end of the day, these two we can add them. If we add them, you see that here becomes 2 integral of 0 to pi on 2 of sine x exponent 6 dx, then minus integral of 0 to pi on 2 sine x exponent 8 dx. And then if we further reduce it, remember we said I of n is equal to integral of 0 to pi on 2 of sine x exponent n dx. So here's 2 I of 6 minus I of 8. So let's first start with I of 8. I of 8 is equal to, let's put it in the reduction formula. So n minus 1, which is 8 minus 1 over 8. So 8 minus 1 is 7 over 8. Then I of n minus 2 is I of 6. So this can further be written as 2 I of 6, then minus 7 over 8 I of 6. So now if we do this subtraction, we'll find out that this is 9 over 8 I of 6. So let's find I of 6 from the reduction formula. I of 6 is equal to 6 minus 1 is 5 divided by 6. Then 6 minus 2 is 4. So here's I of 4. And then I of 4 is equal to 4 minus 1 is 5 divided by 4. 4 minus 2 is 2. I of 2. Then I of 2 is equal to 2 minus 1 is 1. So 1 divided by 2. And then 2 minus 2 is 0. I of 0. So let's find I of 0 from this I of n. So I of 0 is equal to integral of 0 to pi on 2. Sine x exponent 0 is 1. So dx. So I of 0 is equal to, now if you integrate dx, you get x evaluated as 0 and then pi on 2. So I of 0 is equal to pi on 2. So now we can find I of 2. So I of 2 is equal to 1 over 2 times I of 0, which is pi on 2. And this is equal to pi on 4. And then now we can find I of 4. So I of 4 is equal to 5 over 4 times I of 2. And I of 2 is pi over 4. So pi over 4. And this is equal to 5 pi over 16. So having found I of 4, we can find I of 6. So I of 6 is equal to 5 over 6, then times 5 pi over 16, and this is equal to 25 pi over 92. So having found I of 6, all we need to do is to put it in this to find the integral. So this is equal to 9 over 8 then times I of 6, which is 25 pi over 92. And if you do that, you will get 45 pi over 256. And that is exactly what we were supposed to prove. So this other problem is I of n is equal to integral of 0 to 1 of x exponent n, exponent minus 1 over 2x squared dx. Show clearly that I of n is equal to, into bracket, n minus 1, I of n minus 2 minus exponent minus 1 over 2, where n is greater or equal to 2. And then b, it says we should show that integral of 0 to 1 of x exponent 5, exponent minus half x squared dx is equal to 8 minus 13 exponent minus 1 over 2. So what we need to do is I of n is equal to 0, integral of 0 to 1 x exponent n, then exponent minus half x squared. But you see, we cannot easily integrate this. What we can do is that let's model this function and rewrite it as integral of 0 to 1 of x exponent n minus 1. Because I put n minus 1 here, I have to multiply here by x exponent minus half of x squared dx. So there's dx here. So now our u is equal to x exponent n minus 1. And therefore du is equal to n minus 1 x exponent n minus 2 dx. dv is equal to x exponent minus half x squared dx. So v is equal to, if you integrate all of this, you get minus exponent minus half x squared. Now let's differentiate this and see whether our integral is 2. Let's differentiate what is in the exponent. If you differentiate minus half of x squared, you will get minus x, then times, if you differentiate all of this, you will get minus exponent minus half of x squared. So minus minus will cancel, and then we are back to what we started with. So this our v is true. So I of n can therefore be written as I of n is equal to u v. U is x exponent n minus 1. And then v is minus exponent minus half of x squared. Then we are evaluating this as 0 and 1. Then minus v du, which is integral of 0 of 0 to 1 of v is minus exponent minus half x squared. Then du is into bracket n minus 1 x exponent n minus 2 dx. So let's evaluate this as 0 and 1. So you see that here is x. So if we put in 1 exponent n minus 1 is 1. And 1 squared here is 1. So we'll get I of n equals minus exponent minus half. And then if we put in 0, it will make all of this go to 0. But there's minus here and there's minus here. So this becomes plus integral 0 to, plus, let's bring out n minus 1. So n minus 1 then times integral 0 to 1 of exponent minus half x squared, then x exponent n minus 2 dx. So let's just continue from here. So I of n is equal to minus exponent minus 1 over 2, then plus into bracket n minus 1, then integral of 0 to 1 of x exponent n minus 2, then exponent minus 1 over 2 x squared dx. And see that all of this is I of n minus 2. So I of n is equal to minus exponent minus 1 over 2 plus into bracket n minus 1, then I of n minus 2. And that is exactly what we're supposed to prove here. So rewriting this, we see that I of n is equal to into bracket n minus 1, then I of n minus 2 minus exponent minus 1 over 2. So this is our proof. Now, the next thing is that it says we should evaluate 0 to 1 of exponent x exponent 5 exponent minus 1 over 2 x squared dx. So you can see that in this case, n is equal to 5. And we are talking about the case of I5. So now, let's put I5 in the reduction formula. I5 is equal to minus exponent minus 1 over 2, then plus 4I of 3. Then I3 is equal to minus exponent minus 1 over 2, then plus 2I of 1. And then now we cannot go further, so we need to evaluate I of 1 from here. I of 1 is equal to integral 0 to 1 of, that will be x exponent 1, which is x, then exponent minus half x squared dx. But we have already done this. I of 1 is equal to minus exponent minus half x squared, evaluated as 0 and 1. Now, if you put in 1 here, I of 1 is equal to minus exponent minus 1 over 2. 1 squared is 1, so we'll get this. And then if you put in 0, all of this will go to 1, so we'll get plus 1 here. So I1 is equal to 1 minus exponent minus 1 over 2. So we need to take I1, put it back into I3, and then I5, then we can get I5. So we got I1 as 1 minus exponent minus half, but I3 we said is exponent minus half plus 2I1. So we can find I3. So I3 is equal to x minus exponent minus 1 over 2, then plus 2 times 1 minus exponent minus 1 over 2. So this becomes minus exponent minus 1 over 2, and then plus 2 minus 2 exponent minus 1 over 2. So this becomes 2 minus 3 exponent minus 1 over 2. Now we found I3, so let's put it in I5 to find I5. So I5 is equal to minus exponent minus 1 over 2, then plus 4 times I3, which is 2 minus 3 exponent minus 1 over 2. So I5 is equal to minus exponent minus 1 over 2, then plus 4 times 2 is 8, then 4 times minus 3 is minus 12 exponent minus 1 over 2. So I5 is equal to 8 minus exponent minus 1 over 2 minus 12 exponent minus 1 over 2 becomes minus 13 exponent minus 1 over 2. And that is exactly what we're supposed to prove here. So we have this other question here, which is if I of mn is equal to integral 0 to pi over 2 cos x exponent m sine nx dx, we should prove that I of mn is equal to 1 divided by m plus m divided by m plus n, I of m minus 1, n minus 1. So I of mn is equal to integral 0 to pi over 2 cos x exponent m, then sine nx dx. So you see that we can easily integrate nx. So therefore, our u is equal to cos x exponent m. So du in this case, bring m down, then cos x exponent m minus 1. But if you differentiate cos itself, it will give us minus sine x dx. Then div in this case is sine nx dx. So if you integrate div, you get v, which is equal to, if you integrate sine nx, you get minus 1 over n cos nx. So I of mn is equal to u v, which is cos x exponent m times minus 1 over n cos nx, evaluated as 0 and then pi over 2. Then minus integral of v du. V is minus 1 over n cos nx. Then du is minus m cos x exponent m minus 1. Then sine x dx. So I of mn is equal to minus 1 over n cos x exponent m cos nx, evaluated as 0 and then pi on 2. Sorry, here is also 0 and pi on 2. Then it becomes plus, but this is a constant and this is also a constant. Sorry, minus times minus is plus, times minus will give us minus. So minus m over n, integral of 0 to pi on 2. So we have sine x times cos nx, so cos nx sine x, then times cos x exponent m minus 1 dx. So I of mn, let's evaluate this. If you put in pi on 2, cos pi on 2 is 0. And then if you put in 0, cos 0 is 1. So here is only left with 1 over n. Then minus m over n, integral of 0 to pi on 2 cos nx sine x and cos x exponent m minus 1 dx. So let's do this expansion. What is the expansion of sine n minus 1 x? This is the same as sine nx cos x, then minus cos nx sine x. So you see that we have cos nx sine x here. So let's make this the subject. So cos nx sine x is equal to sine nx cos x, and then minus sine to bracket n minus 1 x. So we take all of this and put it into this integral. So we have been able to establish that I of mn is equal to 1 over n minus m over n, integral 0 to pi on 2 cos nx sine x, then cos x exponent m minus 1 dx. And then cos nx sine x is equal to sine nx cos x minus sine to bracket n minus 1 x. So I of mn is equal to 1 over n minus m over n integral of 0 to pi on 2. Now, you see that all of this can be replaced with this. So let me put that in brackets. So we have sine nx cos x minus sine into bracket n minus 1x. All of this will multiply cos x exponent n minus 1 dx. So we can break this integral into 2. So I of mn equals 1 over n minus m over n, integral 0 to pi on 2. So we see that here is sine nx cos x times cos x exponent n minus 1. So if we do that, here's cos x. If you multiply this, we're only going to be left with sine nx and then cos x exponent m dx. And then minus will make here plus m over n, integral of 0 to pi on 2. Then we are going to have sine into bracket n minus 1 x, then cos x exponent n minus 1 dx. So let's rewrite this well. So I of mn is equal to 1 over n minus m over n, integral of 0 to pi on 2, then cos x exponent m, then sine nx dx plus m over n, integral of 0 to pi on 2, cos x exponent m minus 1, then sine to bracket n minus 1x dx. So I of mn equals 1 over n minus m over n. So this is what we started with. You can see that this is I of mn. So all of this becomes I of mn, then plus m over n. All of this becomes I of m minus 1, then n minus 1. Now, let's multiply through by n. We have n I of mn equals 1 minus m I of mn, then plus m I of m minus 1, n minus 1. So what we'll do is that you can see that here's I of mn. So let's bring it to the side. So we have n I of mn, then plus m I of mn equals, then this becomes 1 plus m I of m minus 1, n minus 1. So let's factorize I of mn out. So we are left with m plus n, then times I of mn equals 1 plus m I of m minus 1, n minus 1. So I of mn equals 1 divided by m plus n plus m divided by m plus n, I of m minus 1, n minus 1. And that is exactly what we were asked to prove in the question. So we have this other question here, which is if I of n is equal to integral of 0 to a of x exponent n divided by x squared plus a squared dx, where n is greater than 1, show that n of I of n equals a exponent n root 2 minus into bracket n minus 1 a squared I of n minus 1. And then the last part is evaluate I2 and then I4. So from the question, I of n is equal to integral of 0 to a x exponent n divided by square root of x squared plus a squared dx. So let's rewrite the integral well to write it as integral of 0 to a. Now I'm pulling out x exponent n minus 1. But because I put n minus 1 here, then I have to multiply by x divided by square root of x squared plus a squared dx. So in this case, we can let u to equal to x exponent n minus 1. So du is equal to n minus 1 will come down, x exponent n minus 2 dx. Then div is equal to x divided by square root of x squared plus a squared dx. So v is equal to, now if you integrate this, you see that if you differentiate what is in the square root, it's 2x, and we'll get something which is similar to what is on the numerator. But then I've already done a video on how to integrate rational functions. I will attach it in the description, so you can watch that video to understand how we do this integral. Now if you do this, you get square root of x squared plus a squared. So I of n is equal to, we have u v, so this is our u and this is our v. So x exponent n minus 1 square root of x squared plus a squared, evaluated at 0 and then a, minus integral of v du, and then our v is square root of x squared plus a squared, then times du is n minus 1, and times x exponent n minus 2 dx. Now if you put in a here, you see that here is a squared plus a squared, we will get 2a squared, and if you find the square root of that, you will get a root 2. So I of n is equal to a exponent n minus 1 times, here is a root 2, then minus, now what we can do is that we can bring out n minus 2, so minus, sorry, n minus 1 to bracket n minus 1 integral of, here 0 to a of x exponent n minus 2, then square root of x squared plus a squared, then dx. So if we simplify further, you see that a exponent n minus 1 times a will give us a exponent n. So I of n is equal to a exponent n root 2, then minus into bracket n minus 1 integral of 0 to a, and then x exponent n minus 2 square root of x squared plus a squared, then dx. But what we'll do is that let's rationalize the square root by multiplying by square root of x squared plus a squared divided by square root of x squared plus a squared. We want it to look in the original form that we're given. So we find out that I of n is equal to a exponent n root 2, and then minus into bracket n minus 1 integral of 0 to a, and here becomes x exponent n minus 2 times x squared plus a squared dx, all of this divided by square root of x squared plus a squared. So we can then break this integral into 2. So I of n is equal to a exponent n root 2, then minus into bracket n minus 1 integral of 0 to a. Now if you multiply x exponent n minus 2 by x squared, you get x exponent n divided by square root of x squared plus a squared dx, then plus, sorry, minus into bracket n minus 1 integral of a squared, then times x exponent n minus 2 divided by square root of x squared plus a squared dx. So I of n is equal to a exponent n root 2, then minus into bracket n minus 1 integral 0 to a x exponent n divided by square root of x squared plus a squared dx, and minus integral n minus 1, that I'm pulling out a squared integral of, here 0 to a of x exponent n minus 2 divided by square root of x squared plus a squared dx. So we find out that I of n is equal to a exponent n root 2 minus n minus 1. All of this becomes I of n minus n minus 1 I of n minus 2. So let's expand this. So I of n is equal to a exponent n root 2, then minus n I of n plus I of n minus into bracket n minus 1. Sorry, there's an a squared here which I ignored. So here's a squared I of n minus 2. So a squared I of n minus 2. So you see that this I of n and this I of n will cancel. If we bring this to the left hand side, we get n I of n is equal to a exponent n root 2, then minus into bracket n minus 1 a squared I of n minus 2. And this is exactly what we're asked to prove in the question. Now, the next thing is he said we should evaluate I of 2 and I of 4. So let's start with I of 2. If we put I of 2 here, we find out that this will become 2I of 2 is equal to a squared root 2 minus 2 minus 1 is 1. So minus a squared. I of 2 minus 2 is I naught. So let's put I of 0. Let's find I of 0. I of 0 is equal to integral of 0 to a. Now x exponent 0 is 1. So 1 divided by square root of x squared plus a squared dx. If you do this integral, you are going to get I of 0 equals hyperbolic sine inverse of x over a evaluated at 0 and a. Now, I have already done a video on how to do this kind of integrals. I will attach that video, how to integrate hyperbolic functions. I will attach it in the description. So you can watch it to understand why this is like this. And then when you put in the limits, if you put in 0, hyperbolic sine inverse of 0 is 0. But if you put in a, we are going to get hyperbolic sine inverse of 1, because a divided by a will give us 1. So I of 0 is equal to hyperbolic sine inverse of 1. But hyperbolic sine inverse of 1 is the same as natural log of into bracket 1 plus root 2. So we have been able to establish from the proof that ni of n is equal to a exponent n square root of 2 minus into bracket n minus 1 a squared I of n minus 2. And then we also established that I of 0 is equal to natural log of into bracket 1 plus root 2. And then we are looking for I of 2 and then I of 4. But from the reduction formula, we found out that I of 2 is 2i2 equals a squared root 2 minus a squared I of 0. So we can further simplify this as 2I of 2 is equal to a squared root 2 minus a squared. I of 0 is natural log of into bracket 1 plus square root of 2. So I of 2 is equal to a squared over 2 square root of 2 minus a squared over 2 natural log of into bracket 1 plus root 2. So at the end of the day, we can factorize a squared over 2 out. We are left with natural log of into bracket 1 plus root 2. Then, so I of 2 is equal to, we want to factorize a squared over 2 out. So a squared over 2, then bracket square root of 2 minus natural log of into bracket 1 plus root 2. So if you point this on a calculator, it will give you a certain constant times a squared. Now let's find I of 4. Now if you put 4 in the reduction formula, find out that 4I of 4 is equal to a exponent 4 root 2 minus n minus 1 4 minus 1, which is, so if we put in I of 4 in the reduction formula, we find out that 4I of 4 is equal to A exponent 4 root 2 minus 4 minus 1 is 3 A squared. I of 4 minus 2, which is I of 2. So 4I of 4 is equal to A exponent 4 root 2 minus 3A squared. I of 2 is A squared over 2 times root 2 minus natural log of 2 bracket 1 plus root 2. So 4I of 4 is equal to A exponent 4 root 2. 3A squared times A squared becomes minus 3A exponent 4 over 2. Then times root 2 minus natural log of 1 plus root 2. So let's divide through by 4. But first, let's factorize A exponent 4 out. So we find out that 4I of 4 is equal to A exponent 4. Then a bracket here. Here is left with root 2. Then minus 3 over 2 root 2. Then plus 3 over 2 natural log of into bracket 1 plus root 2. So 4I of 4 is equal to A exponent 4. Now, this becomes into bracket minus root 2 over 2, then plus 3 over 2 natural log of into bracket 1 plus root 2. 4I of 4 is equal to A exponent 4 into bracket 3 natural log of into bracket 1 plus root 2, then minus root 2. All of this divided by 2. So we further divide it by 4. So I of 4 is equal to 1 over 4 times 2 is 8. So 1 over 8, or in other words, A exponent 4 divided by 8 into bracket 3 natural log of into bracket 1 plus root 2 minus root 2. So this is I of 4.